system. This is great. Why? Because we cannot do that within the framework of Newtonian mechanics. You have 5 degrees of freedom in Newtonian mechanics. If you're solving it using F equals ma, if you have 5 degrees of freedom and 2 constraints, how many unknowns will you have at the end? So again, 5 degrees of freedom, 2 constraints within the framework of Lagrangian mechanics. How many unknowns will you have within the framework of Lagrangian mechanics? How many? 3, okay? If you go to Newtonian mechanics, we have 5 degrees of freedom subject to 2 constraints. How many unknowns in total? There are 7. Right? You add, you don't subtract. Okay? Why? Because simply you cannot get rid of the degrees of freedom. You have to keep them and keep the unknowns associated with the constraints. What are these? Constraint forces. These are unknowns. Okay? So there are 7 in total unknowns. And you need 7 equations. Yeah, indeed, 7 equations for them. Whereas here, no, just accept the constraint, and I don't want to bother with its value, the normal force. Okay? So this is a great privilege. But someone might argue that, well, no, you know what, sometimes we want intentionally to know the value of the constraint force. If here is a pendulum rod and you're doing very fast maneuver, then the rod, if it's not stiff enough, it will break. So I need to know how much force this guy is bearing, right? Or in this example, we have a normal force here, right? Maybe this normal force is large enough to break the surface. I intentionally, in this particular problem, I want to know the value of the constraint force. Okay? So Newtonian mechanics will give it for you for sure, right? Because you have to account for it in the first place. Here, if this is your real intention, that's fine. We're going to give you a means to do it. Okay? And now we're going to be close to Newtonian mechanics in the sense that it's your desire. We have 5 degrees of freedom subject to 2 constraints, but you want to know the 2 constraint forces, then it will be 7 unknowns at the end. But still will be also turning the crank, right? This is a scalar function, everything is the same as you might expect. Constraint forces, every force is in the right hand side. So we're going to have here add some terms related to the unknown constraint force. So this is the second classification. So holonomic constraint, you can use it to reduce your system, or if you don't like and you really want to account for the constraint forces, then we're gonna deal with the constraint forces. How to do that? Okay, we're gonna talk about it in a minute. Any questions so far? Any question, please? Okay, so constraint forces. I already did it, but let's ask about it. If this is a constraint, how do you draw the constraint force? It's always perpendicular, right? Very good. It's perpendicular, that's correct. This is your constraint force, F constraint. I want to relate it to the constraint. The constraint is represented by this relation. If psi, some function of the q's is equal to 0. You said the constraint is perpendicular to the surface, and the surface is mathematically represented by this relation. X squared plus y squared equals 0, whatever. So this is perpendicular to the surface. I know the equation of the surface. How you can get its perpendicular vector? So the question is now, I know the constraint surface, some function, I know this function, equal to 0. Okay? I want to get its perpendicular. How can I get that? Because I'm saying that my force will be in that direction. So I want to know that direction first. What is the direction perpendicular to your surface? You have an equation. 200A, you will not pass 200A if you don't know this.
Just take cross
product.
Yeah, dot product.
Or given psi, I don't know, there's no cross, there's nothing here. I have psi, I have the relation. governing the surface. I have the relation representing the surface. And I need to get its perpendicular. Second derivative. Derivative with respect to what? So psi is just a scalar function. Maybe here is psi, x squared plus y squared minus L squared equals 0. This is psi of x and y, right? This is really the constraint of the pendulum. I want to get its perpendicular. This represents a surface. I want to get its perpendicular. How do you get it? Derivative with respect to what? Because it's function of two variables.
Gradient.
Gradient, that's correct. It's the gradient, guys, right? The gradient is the vector pointing to the perpendicular to the surface, for sure, right? And in the gradient, you simply differentiate with respect to all the variables. It's partial x in the x direction, partial y in the y direction, and so on and so on. This is the gradient. So indeed, your constraint force is in the direction of the gradient. Simply, it's a scalar multiple of that dot, right? Because I don't know its magnitude. And of course, this scalar multiple is unknown. Okay? Any question about that? Any question? Please. Like I said, don't let anything.
The gradient is the slope. That's it. Okay.
It is related for sure.
Yeah, then you see that you just use a scalar.
It's perpendicular to the slope.
Yeah.
Okay, so this is my force. Okay, this is your force with an unknown lambda. What can I do? I add here. I need to add to this equation plus something related to your constraint. Well, wait a minute. My F constraint is lambda times nabla psi. Psi is function of q's. Okay. If it's function of x, y, and z, our space, I'll say the gradient will be partial psi, partial x in the x direction. Gradient is a vector, right? So it has components. Partial psi, partial x in the x direction, partial psi, partial y in the y direction, partial psi, partial z in the z direction. This is how you're represented in the x, y, z space. But within the framework of analytical mechanics, we don't work with this space. We work with what? Anybody remembers? Q space, the configuration space, which is simply Q1, Q2, Q3 up to Qn, right? Okay? So, and psi is a function of Q, so it's something like this here in the Q space, actually. So it's gradient with respect to the Q's, it's partial psi, partial Q1 in the Q1 direction, and so and so. The hat is a unit vector, okay? Okay? Any question? Okay, let's come here. I need to add the effect of the constraint force, right? In this equation. What is this equation? This whole equation is for little qj. It's corresponding with little qj. So like I said before, the right hand side, these are the forces in the direction of these guys. So what is the constraint force in the direction of little qj? Can you tell it from here? What is the constraint force in the direction of little qj?
Lambda partial psi by partial qj.
Exactly. So we're done. This is the constraint force. Partial psi, partial qj is known, but lambda is unknown. So lambda represents the unknown force. And if you have multiple constraints, if you have more than one constraint, then fine, then just add them, right?
Lambda 1.
Summation k equals 1 to little m number of constraints k. Okay? And this is the most generalized Lagrangian equation. Can solve any problem. We're going to just divide it a bit now. Any question about that? So lambda is we call it Lagrange multiplier, and we're going to know why later on. So your constraint force you can see here. I'll ask you a question, which if you come to the prelim, I will ask you, though I'm not used to. If you look at this equation, so we're done, okay? You just modify the equation over time. But here is some fundamental question. If you look at this equation, this is a force, okay? A precise scalar function. Within our classification of forces, how do you call this force? Yes, or more generally, it's a monogenic force. It's a force that comes from a scalar. Just give me a scalar function, I'll give it the force, right? I'll represent the force. So this force is derivable from a scalar. Each component of the force simply coming from this guy with respect to that direction. Okay? So holonomic constraints are maintained by monogenic forces. Okay? The forces that maintain holonomic constraints are conservative in nature, are monogenic in nature, come from a single function. Okay, anyway, we're done with this branch, we killed it to death. What about the non-holonomic thing? Any questions so far, please? Any questions so far? So, just give you an example. Well, we have, maybe let's do it 4 degrees of freedom and 1 constraint, right? 4 degrees of freedom, 1 constraint, holonomic constraint. It's up to you. If you want to ignore the constraint and neglect one of the degrees of freedom, you're going to live by 3 by 3 and that's it. No, I want to know the constraint force. Then that's fine. I will apply this equation. How many times I'll apply this equation? I have 4 Q's subject to 1 constraint. The first option is to eliminate and get 3 Q's subject to no constraints. We know how to deal with that. It's not my concern now. I'm now concerned with 4 Q's subject to 1 constraint. I'm not going to eliminate one of the Q's. I'm going to live with the 4 Q's. So how many times I'm going to apply this?
4.
4 times. Very good. And how many unknowns in total do I have?
6.
Why?
2 lambdas.
I said just 1 constraint.
5.
So it's 5. 5 equations, okay? 5 equations. You said we're going to apply this 4. What's the 5th equation to make closure?
Lambdas.
It's the force equal to the sine.
No, I already substituted here.
Oh, okay.
Because what are the 5 unknowns first? What are the 5 unknowns?
Q's
4
and 1
degrees of
lambda.
freedom and lambda, right? Okay. So I need 5 equations, please. 4 coming from dynamics. What's the 5th?
That one.
What?
Red one.
The constraint force, the constraint equation, right? The constraint, x squared plus y squared equals L squared. This is an equation given to you, right? Okay, so this is how we deal with things. Of course, we're going to do very specific examples and solve it, show how to do it, guys, but just to have a big picture. Non-holonomic constraints. You cannot represent them in this form. They are typically written in this form. The kth constraint is written in this form. Summation A. This might be function of Q's times Qj dot. So what do you mean? I mean that they are inherently written on velocity. They are constraints on the velocity, not on the position. Holonomic constraints are written on the position. I constrain your position in a certain way. For the pendulum, you have to move along a circular path. For this guy, you have to move along this parabola or whatever. So it's a constraint on the position. Some constraints are not on the position, but rather on velocities. I'm going to constrain your velocity vector to be in some direction, or prevent your velocity vector from having component in some particular direction. Okay? So this is the very fundamental difference between holonomic and non-holonomic. The very well-known example is your car. A rigid body in the plane has 3 degrees of freedom, x, y, and theta, right? So, x, y of the center of mass, and this is theta, and here is your axis. Your car are not allowed to move sideways. Your car is constrained to move along its axis only. Right? So this is a constraint on the velocity. In other words, your velocity vector of your car is not allowed to have a component in that direction. The component of your velocity vector along that normal direction is 0. This is your constraint. Okay, so let's write it. So along that direction, my velocity vector has 0 component. Okay, so you know, I'm moving x dot in that direction, y dot in that direction, and this is theta. Can you give me the component in the along the red line, please? So again, this is theta. So y dot cosine theta, and then negative x dot sine theta equals 0. This is your non-holonomic constraint. It's a constraint that is inherently written on velocities, doesn't constrain the position of the car. I don't care about the x, y, and theta, right? But I prevent your velocity vector from having components in direction. I constrain your velocity vector. Okay? So simply, you cannot write this guy as some function of x, y, and theta equals 0. You cannot do that. I cannot write it as psi of x, y, and theta equals 0. You will not be able to do that. Okay? In other words, you cannot integrate that constraint. Any question? Yes, Anshul.
Sorry, do you just go over real quick what is the definition of a non-halogenic constraint?
Non-holonomic constraint is typically written in this form, which is some coefficient times the velocity is equal 0. So it's mainly written in terms of velocities, not positions. So it's a constraint on velocities.
Oh, okay.
You can see here in this red equation, it's a constraint on x dot and y dot. This relation is not between x, y, and theta, but between x dot and y dot, right?
But A, we don't know A, variable that we don't know.
Say it again, please.
The AQ.
Yeah, so,
Something we don't know.
no, they are known.
Yeah, no.
Yeah, I mean, relate this to the general form. The A's are the coefficient of your velocities.
Okay.
So this is the A corresponding to y dot is cosine theta. The A corresponding to x dot is negative sine theta, right? These coefficients are known, that's fine. Another example. So I think I'll stop here, and you probably know why. Because I